Doing a space mission is a highly interdisciplinary undertaking. We are dealing with very complex systems, and to be successful with such systems, we really have to cover all relevant disciplines.
Everything from the start of a mission or the development of a mission until the end of a mission, where we also are analyzing the science data.
So that's why we joined forces and founded the Space Research Center here at the Bundeswehr University in Munich.
The Space Technology Lab is a lab where we are developing space technology, but on the other hand we are also involved in actual space missions.
So we're looking really at mission analysis, how we can fly from Earth to somewhere. We're looking at spacecraft design, which of course is highly connected on mission analysis or with mission analysis. We're looking at specific technologies for the spacecraft, making spacecrafts more autonomous. For example, having autonomous landing technology, looking into how to make spacecrafts more performant in terms for scientific instruments, especially very stable. Scientific instruments are very sensitive, and the spacecraft need to be very quiet. So we are working on technologies to make the spacecraft a quiet environment for experiments. And we are looking into specific experiments on scientific spacecrafts which fly to other planets, measuring gravity fields, measuring atmospheres, where we are involved in several missions.
In this lab we do space propulsion and particularly electrical propulsion. The advantage of electrical propulsion system that it produces very high-speed particles, and thrust is mass flow times velocity of the particles, so we can save considerably on mass in an electric propulsion system compared to a chemical equivalent. A micronewton thruster is, for example, a vacuum arc thruster which has a solid propellant. It is evaporated using an electric arc, and we create a high-velocity metal jet. And this is used for communication in space to position satellites very precisely. A vacuum arc thruster was used in a nano-satellite project called CubeSat, where we built a 10 by 10 by 10 centimeter small satellite, and we integrated a vacuum arc thruster for positioning purposes.
We are the Space Communications Lab at the Space Research Center. Our job is to maintain a reliable, fast and a secure communication channel to geostationary orbit satellites and the International Space Station. Mostly what we do is we design and shape signals which can be efficiently, fastly and reliably in a very secure manner be transmitted to the satellite and received back as well. How do we do it? As part of any research, we start at the basic, the math. We start with designing algorithms. Once the algorithms are designed, they are thoroughly tested through simulations. Once we are sure that they're working in our simulations, we put them to the test in our lab. Okay, we have the equipment and the personnel to perform true over-the-air testing for satellite algorithms, equipment, and technology. We have basically 3 very huge antennas from diameters 5 meters up to 7 meters, and we can communicate in all frequency bands to all the possible satellites within our view or sight or even beyond. We, the Space Communications Lab, were part of a very huge project related to the International Space Station. The name of the project was Icarus. We did certain channel measurements, and once they were done, we provided this scientific data to the authorities or the people responsible for making these antennas. And recently, this project became a success, and the antennas were successfully installed on the International Space Station.
Preparatory steps to install this Icarus antenna unit. Once installed, it will be followed up by the installation of this cable harness.
In the Navigation Lab, we're working mainly in activities related to GNSS, Global Navigation Satellite Systems. Particularly, we focus in Galileo, which is the European GNSS. So, for example, we have developed and optimized the Galileo first generation signals, which are currently in use and can be received by the newest smartphones. GNSS cannot offer always the centimeter level accuracy that is needed for certain applications, like autonomous driving. And that's why we have developed our own receiver, which is the most advanced research receiver, and in which we are integrating other sensors. So we are doing sensor fusion. One of the sensors that we're really focused right now is Lidar. And this sensor we don't use only for terrestrial applications, but also space applications. So one of the examples of this sensor in space applications is autonomous navigation about small bodies in space, like asteroids or asteroid landing. So we have relative navigation algorithms in the PC running on board the UAV, and the UAV is supposed to fly around a small body using the algorithms that have been developed in the institute.
Our department, the Space Lab, is involved in the radio science experiment on Rosetta. The science objectives of the radio science experiment are the gravity field of the comet Churyumov-Gerasimenko, and with the so-called biostatic radar observations, we are estimating the dielectric constant of the surface. It was the first time we were able to directly measure the mass loss during the perihelion. So the New Horizons flyby in 2015 was a historical moment. We were involved in the measurement of the Pluto system mass and also of the individual masses of Pluto and Charon. We can measure the velocity of the spacecraft, and due to the velocity change of the gravitational attraction of Pluto and Charon, the spacecraft velocity is changing. And with that, we can go back and estimate the mass which is pulling on the spacecraft. Looking at asteroids, we can estimate the mass of the asteroid, and from this we can learn the density, the internal structure, and this is also possible with our experiment. We can use the knowledge we are gaining from the space missions we are involved for teaching and to teach the students the real-life project.
This is the Library Structure Lab. In this lab, we conduct several tests on structural measurements and structural loads, which means we have here huge machines conducting forces on different materials, and we are just measuring how much they can take. FLOMESS is an abbreviation for Flight Loading Measurement System. So we are measuring strain or flight loads during the ascent of the rocket, collecting them and send them back to Earth. This FLOMESS module can be installed into sounding rockets to provide us with exact structural loads. We are participating in the program so-called REXUS-BEXUS. REXUS means Rocket Experiments for University Students. This program is provided by the European Space Agency and the German Space Agency. Spaces on 2 rockets, and one of the spaces is the experiment module FLOMESS.
What it really excites me is that in our world, it just not stays in theory or just in a concept, but actually we are able to test it. Like we have the drone and we are able to test our relative navigation algorithms. We are constructing our own testbed in order to see if actually what we have proposed works.
The work we do here enables technologies for deep space missions, and we can make satellites work more efficient and more compact.
With the data we are analyzing here at the university from several space missions, we are increasing the knowledge of our solar system.
This research center now is a very good basis for a cooperation, bringing all the disciplines together, and by this, working on details, having the whole mission in view, we can create really innovative solutions for payloads, for subsystems, also for science.